Welcome to my poster. My name is Mirte Eyden and I'm a PhD student at the University of Innsbruck. I would like to tell you something about exciting recent work that I've been doing together with Gemma de las Cuevas and Tensor. Our work is related to two open problems, one in mathematics and one in physics. Let me start by explaining to you the math problem.
We see here a picture of the set of all positive linear maps. There are linear maps, P, that map square matrices in dimension D1 to square matrices in dimension D2. A map is called positive whenever it maps PSD matrices always to PSD matrices. The question is now, given two copies of a positive map, is the tensor product P tensor P still positive? It turns out that this is not always the case. You see here the subset of all two tensor stable positive maps, for which P tensor P is still positive. We can now ask the same thing for three copies. What we find is that the subset is again strictly smaller. This can go on. And the question is now, which positive maps will stay positive under all tensor powers? They are called tensor stable positive maps. Well, some of them are known. The completely positive and completely co-positive maps are tensor stable positive. We will call them the trivial examples. However, it is not clear whether there are more. Is there a subset, indicated in the orange, that contains more than just the trivial examples? Are there non-trivial tensor stable positive maps?
The problem of tensor stable positivity is related to a very interesting and important problem in quantum information. It is unknown whether some quantum states with a very specific property, depicted in the orange again here, it's unknown whether they exist. And actually existence of non-trivial tensor stable positive maps would imply the existence of these special quantum states. Our research on this topic goes in two directions, and the first direction is about quantum halos. Let's go into that.
We consider the problem on a different field. Instead of the reals, we use the hyperreals, the field used in non-standard analysis. Or, to be more precise, instead of the complex numbers, we use a complexification of these hyperreals, called the hypercomplex numbers. The upshot of this is that on the hypercomplex field there exist infinitesimal numbers that form a halo around the normal complex numbers. When we consider the set of positive maps again, but now on the hypercomplex numbers, they will also have halos around them, consisting of maps that are infinitesimally close. This happens in particular for the trivial maps. At the boundary, however, this halo will now shine into the orange area. With this, we can answer the question, are there non-trivial tensor stable positive maps on the hypercomplex numbers? With yes. For the problem in quantum information, working on the hypercomplex means that we cannot really talk about quantum states anymore. Instead, we call them quantum halos. Also here, because of the halos, we can prove existence of the specific quantum halos whose existence is still unknown for the normal complex numbers. The second line of our results is about undecidability. Instead of asking the question, are there any non-trivial tensor stable positive maps, we reformulate the problem as a decision problem. Given a positive map P, is it tensor stable positive? We study the computational complexity of this problem, and we prove undecidability of a very related problem, namely, given a map P on a specific input called the matrix multiplication tensor, is this tensor stable positive? This problem is undecidable.
I would love to tell you more about it when you come to my poster, and I would be happy to answer all of your questions. See you then.